This presentation is for GRS-IBS and emerging seismic bridge technology. IBS consists of three main components. 1. Reinforced soil foundation. 2. GRS abutment. And 3. Integrated approach. The salient and different features of GRS and MSC are: 1. The internal angle of friction for MSC shall be less than 40. For GRS, it can be greater than 40. The spacing of the reinforcement for GRS shall be less than 300. For MSC, it can be more than 300. In extreme event 1 limit state, there is a 50% traffic load surcharge on MSC, whereas there is no considerations of traffic load required for GRS. The fundamental difference between GRS and MSC is MSC follows column earth pressure theory with a potential failure surface, whereas for GRS, it is a composite section. Layout of GRS-IBS requires the beam seats to be greater than 610 mm and service bearing pressure less than 200 kPa. The setback AB greater than 200 mm, the clear spacing between facing blocks and beam DE greater than 76 mm, the abutment base with B total sum of B plus facing block width. Depth of reinforced soil foundations shall be greater than 460 mm and the length shall be 1.25 B total. For slope cuts to 45 degrees, the reinforcement shall progressively increase to 0.7 H. The three internal stability checks are: 1. Bearing resistance. 2. Deformation. 3. Required reinforcement strength. The three external stability analyses are: direct sliding, 2. Bearing capacity, 3. Global stability. GRS-IBS has an inbuilt 0.4 G seismic capacity. The design requires soil parameters for foundation soil, retained soil, reinforced soil, load base unit weight, and reinforced soil foundation. The design informations required are the scour elevations, the height of the abutment, the length span of the bridge, which allows the following informations to be obtained. Other parameters are the spacing of the reinforcement, the height of the bridge, and the informations of spacing elements. This allows the reinforced foundation soil to be obtained. Finally, is the specifications of geosynthetic reinforcement. The bridge load allows the footing bridge seats dimensions to be calculated, and the service bearing pressure shall be less than 200 kPa. The following are the load and resistance factor to be used for subsequent calculations. The design of required reinforcement strength involves converting the traffic surcharge on the approach pavement to an equivalent earth overburden. This calculation is abutment height dependent. Similarly, for road base, it is converted to a surcharge which is bridge height dependent. The summary of the surcharge is as shown. The various stress profiles are summarized as follows: live load of the bridge, dead load of the bridge, cell width of the approach pavement, live load on the approach pavement, reinforced backfill and GRS abutment, retained soil, stress distribution. The factored required reinforcement strength at a given depth is the sum of all the factored various stresses, but not including the stresses from the retained soil. The lateral stresses are calculated as follows. For the reinforced soil, it is the product of a factor of 1.5 by the density, by the depth involved, by the active soil coefficient. For the approach pavement, it is a product of 1.5 by the dead load, by the active soil coefficient, and for the live load on approach pavement is a factor of 1.75 by live load by active soil coefficient. To simplify the calculation, the load on approach pavement were considered to be continuous and need to be subtracted when calculating the stress due to the bridge load. The center line of the bridge load is the point of interest in the calculations of the stress due to the bridge. The stress due to the bridge is the product of a factor of 1.25 multiplied by dead load plus a factor of 1.75 multiplied by live load. This is to be subtracted from the load due to the approach pavement to account for the continuous of loading assumptions made. Since the load are not continuous, the Bose-Nash theory is applied in the calculations. This allows the total stress to be calculated. With all the stresses of interest obtained for a given depth, the required reinforcement strength can be calculated, and it shall be less than the factored ultimate reinforcement strength. Each calculation shall be carried out for every reinforcement layer. Fortunately, all the calculations are in an Excel spreadsheet available from FHWA. Designing GRS abutment based on extreme event 1 limit state of H2 involves the selections of seismic parameters. The inertial force is the product of density by the height and a half by the external horizontal seismic coefficient. For dynamic force is the product of density by the total height square by the difference of Mononobe-Okabe earth pressure minus the active soil parameters. The summary of load and resistance factor for strength 1 and for extreme 1 is as shown. The dimensions of the reinforced soil foundation is the minimum excavation required. However, to accommodate for the construction tolerance achievable, the excavation dimension shall need to be increased accordingly. In the installations of geotextile for reinforced soil foundation, the first sheet is installed on the upstream. Subsequent sheets are installed with a 610 mm overlap. This is to ensure that the overlap at the top prevents the water from flowing into the reinforced soil foundation. In the constructions of reinforced soil foundation, the reinforcement shall be pulled tight before placing the structural field. The structural field, well graded, shall be placed from the front face to the back. Every 300 mm of field shall require an additional layer of reinforcement. Once the required depth of the reinforced soil foundation is achieved, a leveling pad at the abutment and the wing wall location shall be prepared. This is followed by wrapping the top layer of the geotextile to enclose the reinforced soil foundation and the installations of rock geotextile apron. The first course of the facing block shall be laid level. This is followed by the base reinforcement. The structural field below water level shall be open graded, and the field shall be placed from the front face to the back. A filter membrane between open graded field and the retained soil shall be required. The field above water level shall be well graded with a filter membrane at the facing block interface. For compaction requirement, no compaction is allowed above the facing element. Only handheld mechanical compaction equipment is allowed within 600 mm adjacent to the facing element. A walk behind mechanical compaction to be 600 mm from the facing element. All compaction shall be carried out parallel to the facing element. Compaction perpendicular to the facing element is prohibited. In conclusion, GRS-IBS is an accelerated bridge construction. Potential cost saving up to 50%, no specialized labor and equipment required, lower maintenance costs. It can be used as temporary access in the midst of its construction. It is an open system, simple design, potential alternative for box-covered through bridge abutment deep foundation, and last but not least, suitable for seismic applications. Acknowledgement and references. End of presentation.